Okay, so today we are going to talk about electric potential. So we introduced electric fields, which is the force per unit charge, and electric potential is the potential energy per unit charge. So if you remember back from Physics 1, force and potential energy are fairly closely related. So we're going to talk a little bit about that today. And we're also going to talk about the relationship between electric potential and electric potential energy. So let's start our lecture with a review of some of the basic principles in mechanics in Physics 1. So when we talked about conservative forces, these are forces for which the total mechanical energy, the sum of kinetic plus potential, is conserved. And so for conservative forces, the work done by these conservative forces is equal to the negative of the change in potential energy. So if you increase an object's potential energy, you are doing negative work. And if you decrease an object's potential energy, you're doing positive work. And so that's an important thing to keep in mind. And that only applies for conservative forces. So if an object is was thrown in the air, as it's increasing its height, its potential energy is increasing. Gravity is doing negative work, it's slowing it down. And when the object reaches the top of its trajectory and starts to fall, then it's losing potential energy, and gravity is now doing positive work. And that comes from the fact that gravity is a conservative force. For non-conservative forces, the work done is equal to the change in kinetic energy plus the change in potential energy. So if I lift this pin, I am doing work on it, not because I'm giving it velocity and changing its kinetic energy, but because I'm lifting it and giving it potential energy. So I'm doing work in that case. And for all forces, the net work done by all forces is equal to the change in the object's kinetic energy. So is the work energy theorem, that the net work done by all the forces, whether they're conservative or non-conservative, is equal to the change in the object's kinetic energy. And now we're going to apply that to electricity. So electric field is the force per unit charge, and electric potential, which we're going to define, is the potential energy per unit charge. So let's consider a test charge, QT, in an electric field. The field does an amount of work equal to, and so the general definition of work, again going back to Physics 1, is that work is equal to the integral of the dot product of F dot and dr, where dr is the differential element of displacement, and so you're integrating over the entire displacement, the dot product of force and the displacement. Now, force is equal to Q times E, so you can also write that as Q is equal to the integral of E dot dr. And since it's a conservative force, and we're assuming it's the only conservative force acting, that work done is equal to the negative delta U. So the work done is equal to the negative of the change in potential energy, again, because it's a conservative force. But if it's only the electrical force acting in the problem, then from the work energy theorem, that work is also equal to delta K. So it's equal to negative delta U, and it's also equal to delta K. So let's look at this in terms of the change in potential energy delta U. Delta U in this case is equal to negative delta K because there's only the conservative force acting, which means it's equal to the negative of the work done, which means it's equal to the negative of the test charge multiplied by E dot dr. So the electric field vector dot the displacement vector. And so we can then define the change in electric potential as the change in potential energy per unit charge of the object in the field. So we'll define the electric potential as being equal, delta V, as being equal to delta U over QT. And we can also write that as the negative of the integral of E dot dr. And so that's the formal definition of the electric potential. So negative the integral of E dot dr. But you can also write that as the change in electrical potential energy divided by QT, the test charge, the a magnitude and sign of the test charge. And again, it's very, very important when you're talking about electrical potential to keep track of positives and negatives. So the unit of electric potential is the volt, and you might be more familiar with the term voltage. And voltage is just the electric potential. So if you're talking about a battery or a power supply, they are creating a potential difference. And if you connect a circuit to that battery or to that power supply or to whatever else you may be connecting it to, a current will flow through it. We won't get to current. We'll talk a little bit about current next time, but we won't really get to currents until we get to chapter 25. So the unit of electric potential is the volt, 1 joule per coulomb. The electric potential, like the electric field, only depends on the source charges that create it. So you're dividing the potential energy by the test charge, but ultimately it's the source charges that create the potential difference. And then the test charge, if it's moving through the electric field, that's equivalent to saying it's moving through a potential difference. And another thing to keep in mind, the electric potential is a scalar. It's not a vector like electric fields. And sometimes when you get to more complicated problems, it's easier to figure out the scalar than it is to figure out the electric field. Because with the electric field, you're basically working in 3 dimensions. And so there are 3 equations that you need to, you're solving for each of the 3 components, whereas with potential, you're only solving for one thing. So we're now ready to look at an example. So what potential difference is needed to stop an electron that has an initial velocity v is equal to 5.0 times 10 to the 5 meters per second? So let's go to the whiteboard and solve this. So we have an electron, negatively charged. It's moving in a potential difference, but we want to stop it. So let's look at this qualitatively first before we get to the math. So there are 2 things, basically, well, 3 things that you can do that would slow down the electron. One is you could put positive charges behind it, which, again, positive charges attract the electron. So as the electron's moving away from the positive charges, it'll be slowed down by the attractive force. So that's one way you can slow down the electrons. Another way is to put negative charges in front of it. And so the electron is heading towards the negative charges which are repelling it. That will also slow it down. And the third thing you could do is some combination of the 2. So you have positive charges behind it and negative charges in front of it. And either way, or no matter how you do it, you're slowing the electron down. And the idea is that you're bringing the electron to a stop. So how does this look mathematically? Well, we know that the force is pointing to the left. So we have an electrical force pointing to the left, but it's a negative charge. So that means the electric field is pointing to the right. And again, electric field points out of positive and towards negative. So we're asked in this problem, what potential difference is needed to stop an electron that has an initial velocity? Okay, so now let's look at this mathematically. So the potential difference is equal to negative U divided by the test charge. So this is the change in potential energy divided by the test charge that's moving within the field, and that includes the sign. So the bottom number is going to be negative, and it's the charge of the electron, but we'll get back to that. So we don't know delta U directly from the information, but we know, since it's only the conservative force acting, that delta U is equal to negative delta K. So we can write this as negative delta K over Q sub T. So now we have enough information to work with. Delta K, and don't forget delta K is also a negative number. So notice you're going to have three negative numbers working in this. So it's losing kinetic energy. So delta K is equal to negative 1/2 m times the initial velocity squared. So it starts with a certain amount of kinetic energy and it ends with 0 kinetic energy because we're told we're stopping the electron. So its velocity at the end is 0. So it loses a kinetic energy equal to 1/2 mv0 squared. And then you're dividing by the test charge again. And so you have negative 1/2 the mass of the electron, and if you don't know this, I'll tell you that. That's 9.11 times 10 to the negative 31 kilograms. We are told that the velocity initially is 5.0 times 10 to the 5 meters per second. So 5.0 times 10 to the 5 meters per second, and don't forget, you're squaring this. So it loses that much kinetic energy, which means it gains that much potential energy, and you're dividing by QT, and the sign matters. So it's negative 1.6 times 10 to the negative 19 coulombs. So that's the charge of an electron, and so we went over that in chapter 21. So you plug all those numbers in, and you solve for the potential difference. So notice you have three negative signs, so two of them cancel out, so you still have a negative. But otherwise, it's, so you have a negative, and then you plug in the numbers. So that's half times the mass of the electron times the velocity which we're given, squared, and then divided by the charge of the electron. And you get negative 0.71 volts. And so that is the potential difference. So it's a negative potential difference. So you lose potential when you're going from away from positive charges and towards negative charges. And similarly, you gain electric potential when you're moving towards a positive charge and towards positive charges and away from negative charges. So hold that thought. We will get back to it. Okay, so now let's get back to our lecture slide. So that was one example, and now let's look at another example. And so this is also in the book. This is problem 3 in chapter 23. So again, it involves an electron. An electron acquires 5.25 times 10 to the negative 16 joules of kinetic energy one is accelerated by an electric field from plate A to plate B. So what is the potential energy between the plates, and which plate has a higher potential? So the second part is actually easier to solve. So we'll look at this qualitatively first, just like we looked at the last one qualitatively first. So for this problem, we have an electron, and now it's accelerating. So for it to be accelerating, you could have repulsive negative charges behind it, or you could have attractive positive charges in front of it, or some combination of the two. And what that means is that the electron is moving away from negative and or towards positive. That means it's gaining electric potential. So we know that delta V is greater than 0, and so point B, since it's moving from point A to point B has the higher potential. So we've established that, or plate B rather. And so we want, what is the potential energy between the plates? So the potential energy between the plates, and we're given the kinetic energy. So if it's gaining kinetic energy, it's losing potential energy. And so it's again, since the only force acting on it is the conservative electrical force, if it's gaining 5.25 times 10 to the negative 6 joules, negative 16 joules of kinetic energy, it's losing the exact same amount of potential energy. So delta V is equal to, or rather delta U, excuse me. So we know delta V is positive, but delta U, and we're not actually asked to solve for delta V, although we could, but delta U is equal to negative 5.25 times 10 to the negative 16 joules. So it gains kinetic energy, but it loses potential energy. So delta U is negative, but we're talking about a negative charge as well. So it's negative divided by negative, which means, or when you're talking about electric potential, delta U is negative, the test charge is negative, so you divide the two together, you get a positive value. So delta V is positive, it's greater than 0. And qualitatively, we saw that here, that it's going from point A to point B, and that delta V has to be greater than 0 for the electron to accelerate, the negatively charged electron to accelerate through that potential difference. So now we're going to talk about the relationship between electric field and electric potential further. So we found that you could calculate the electric potential if you knew the electric field as a function of position by integrating. You can work the other way as well, that if you know the electric potential as a function of position, you can differentiate that and figure out the electric field. So the x component of the electric field is equal to, and you'll notice if you haven't taken or aren't taking Calculus 3 right now, you might not be familiar with that symbol, this symbol right here. That symbol represents partial differential or differentiation. So what you're doing is, let's say f or v rather is a function of x, y, and z. To figure out the x component of the electric field, you're taking the derivative of v with respect to x as if y and z were constant. And so that's called the partial derivative. So the x component of the electric field is equal to the negative of the partial derivative of v with respect to x. The y component of the electric field is equal to the negative of the partial derivative of v with respect to y, and the z component of the electric field is equal to the negative of the partial derivative of v with respect to z. If you're not looking at standard x, y, z coordinates, but instead you've got something with spherical symmetry, and if you're talking about a point charge or some sort of spherically symmetric charge distribution, then the component of the electric field in the radial direction, which means either radially into the center of the sphere or radially out from the center of the sphere, is equal to negative dv over dr. And again, we're assuming spherical symmetry, so there's no angular dependence. So if you just know the potential as a function of r, figuring out the radial component of the electric field, you just take the derivative of the potential with respect to r and take the negative of that derivative. And that gives you the component of the electric field. If you have a uniform electric field in the x direction, then you can write E as being equal to the negative of the change in potential divided by the change in position. And so that's the x component of the electric field. And that's, so it can be positive or negative. The significance of the negative sign is that E points in the direction of decreasing potential, and you saw that in the previous two examples. And if you didn't notice that in those two examples, I recommend going back and rewinding this and taking a look at those two examples. That the electric field always points out of positive towards negative, but potential increases as you approach positive charges and decreases as you approach negative charges or moves away from positive charges. So E points in the direction of decreasing potential. So another consequence of this relationship is that E can also be expressed in volts per meter. And so an electric field of 1,000 newtons per coulomb and an electric field of 1,000 volts per meter are exactly the same. And so that's an important thing to keep in mind. Depending on the problem, you may see the units expressed one way or the other way, but they're actually equivalent to each other, even in SI units. So let's do another example. Thunderclouds typically develop voltage differences of about 1 × 10⁸ volts. So what happens in a thundercloud is that there's friction between the water droplets and the air. And it's kind of like friction if you're rubbing your hair with a balloon, for example. The charges will jump. And, if you have droplets brushing past each other, charges will jump from one to the other. And what typically happens is that you get a potential difference. You get an accumulation of, if there's a lot of motion in the clouds, and this is typical of a thundercloud where you have a lot of vertical motion, that you have a strong updraft in one location and a downdraft in another location. And so what happens is you get an accumulation of electrons in one place, which is equivalent to a negative terminal, and you get a shortage of electrons in another location, which is equivalent to a positive terminal, and you develop a potential difference. So given that an electric field of 3 × 10⁶ volts per meter is required to produce an electrical spark within a volume of air. So again, air is an insulator, so it takes a pretty large potential difference for charges to move within the air. But thunderclouds can get those charges fairly easily, or get to that electric field strength fairly easily. So given an electric field of about 3 × 10⁶ volts per meter is required to produce an electrical spark within a volume of air, estimate the length of a thundercloud lightning bolt. And then can you see why when lightning strikes from the cloud to the ground, the bolt actually has to propagate as a sequence of steps. So let's draw this out. So we will clear this. And so what happens is we'll call it the y direction. We'll assume for the sake of argument that the the lightning discharges in the vertical direction. So EY is equal to negative delta V over delta Y. So we want to find what delta Y is. And so delta Y is equal to the negative of delta V over the electric field. So, and the negative sign doesn't really matter all that much here. So the voltage difference is about 1 times 10 to the 8 volts. So 1 times 10 to the 8 volts. And you're dividing by the electric field, which we said was about 3 times 10 to the 6 volts per meter. And so we want to find what delta Y is. And so that's 1 times 10 to the 8 volts divided by 3 times 10 to the 6 volts per meter. And so that gives negative 30 to one significant figure meters. Now, when you're talking about really tall thunderclouds that go all the way up into the stratosphere, 30 meters isn't that large of a number. And so you have the electric field jumping by a certain amount, but it doesn't get all the way down or all the way across. So what happens is the electric field, or rather the lightning discharge, moves in jumps. So it'll jump a little bit, then it'll jump a little bit more, and then it'll jump a little bit more, and so on. So the lightning is a series of steps, and that's why lightning tends to look jagged. If it was one step, it would be a perfectly straight line. But lightning discharges look jagged because it's a series of straight lines. And so that's an important thing to keep in mind, so that you have a series of jumps, but that doesn't fully discharge or cover the full potential difference that's been created. So you need to keep these things in mind. And so that's why lightning is jagged. It's actually a series of discharges that happen in very rapid succession, but it's not one charge from point A to point B covering the entire potential difference. Okay, let's get back to the lecture now. So now we have another example. The electric field between two parallel plates connected to a 45-volt battery is 1300 volts per meter. Now, this is something that's going to come back into play when we talk about capacitors in the next chapter. And so we have two parallel plates. They're connected to a 45-volt battery, and so there are 1300 volts per meter between them. How far apart are the plates? So let's visualize this again. So when you have two parallel plates, if you have a positive plate and a negative plate, so the electric field is going to move from the positive towards the negative. And so if you remember from what we talked about with Gauss's law, that if you have an infinite sheet of charge and the parallel plates, as long as you're not very close to the edge, for the parallel plates, the electric field between the sheets of charge is going to be uniform and, to an excellent approximation. So the electric field is going to equal negative delta V over delta X. So we know that given this configuration and assuming the X direction goes off to the right, that you're going from decreasing potential the way this is drawn from positive to negative. So, and we're asked to find what delta X is. And so delta X is the width of the plates. And so delta X is equal to negative delta V over E. And so again, remember, we're losing electric potential going from positive to negative. So it's a 45 volt battery, which means the potential difference is 45 volts. So that becomes negative 45 volts divided by the electric field, which we are told is 1300 volts per meter. So 45 divided by 1300 volts per meter, and that tells us the that gives us, and so it's negative, and again, it's negative 45 volts because you're going from positive to negative. So delta X is positive, and it's equal to 0.035 meters, which you can write as 3.5 centimeters. So the sheets have are separated by 3.5 centimeters. You put 45 volts across them, and that gives you an electric field between the sheets of 1300 volts per meter. Okay, so one last example before we get to talking about potential, due to point source charges. So this example, we were asked to show that the electric field from a single point charge follows from V is equal to 1 over 4 pi epsilon naught Q over R. So that's the potential of a point charge. We'll talk about that in a bit more detail in a couple of minutes, but we're going to show how the electric field comes from that. Okay, so let's go to the whiteboard and look at this. And this just shows you how working with derivatives work, or working with the gradient works. So that we have V is equal to 1 over 4 pi epsilon naught. And again, 1 over 4 pi epsilon naught is just the Coulomb constant K, multiplied by Q divided by R. And so the electric field, or at least the radial component of the electric field, and if it's positive, it means it's pointing away from the center or away from the charge. And if it's negative, it's pointing towards the charge. So that's equal to negative dV over dr. And again, we're assuming it's either a point charge or a spherically symmetric distribution. So that's equal to negative Q over 4 pi epsilon naught times the derivative with respect to R, of 1 over r. So this derivative is just equal to negative 1 over r squared. Remember, 1 over r is r to the negative 1 power. So the derivative of that is negative 1 times r to the negative 2 power. So that becomes negative 1 over r squared. So you can write this as being negative 1 over 4 pi, or rather, the negatives cancel. So it's positive 1 over 4 pi epsilon naught q over r squared. So if q is positive, the radial direction is out of the, away from the positive charge. If q is negative, then it's into the charge. And so that's what that means. And so if it's pointing into the charge or into the center of the circle, the radial component is negative. If it's pointing out, the radial component is positive. And so, that's an important sign convention. And again, don't forget that K, the Coulomb constant, is equal to 1 over 4 pi epsilon naught. So you'll see those used interchangeably. So now we're going to talk a little bit about the electric potential. Now, there's an advantage to working with the electric potential in solving comparatively difficult physics problems, in that sometimes, because the potential is a scalar and electric field is a vector, sometimes if you want to find, calculate the electric field due to a broad distribution of charges, sometimes it's easier to calculate the potential first and then use the equations I showed before to get the components of the electric field than it is to calculate the electric field directly. But let's look at the potential due to point charges. And so the previous example is related very much to this. So consider a source charge QS that creates an electric field. If you, instead of looking for the change in V, instead of looking for delta V, if you're looking for the value of V or the voltage at a specific location, you need to define where 0 is. And much like with gravity, and for the same reasons, ultimately you're talking about an inverse square relationship with the force. And when we, in physics 130, when we talked about gravitational potential energy, we talked about the most convenient place to define the potential energy to be 0. And with gravity in the universal sense, the easiest place to define 0 is at infinity. And that's true for electrical potential as well. And when we get to electrical potential energy in a couple of minutes, it's the same thing, that it's easiest to define a potential of 0 at an infinite distance. And so the potential defined relative to 0 at infinity is equal to K, the Coulomb constant, again, which is equal to 1 over 4 pi epsilon naught, times the source charge, divided by the distance r you are away from the source charge. And notice there are no absolute value signs around the source charge. Its sign matters. So if it's positive, the potential increases as you approach it. If it's negative, the potential decreases as you approach it. So there are no absolute value signs on QS. And much like with potential energy, usually you're more interested in the change in potential than its value at a specific location. But sometimes you want the value at a specific location, and that's where this equation comes in. So let's do another example. A point charge Q creates an electric potential of positive 185 volts at a distance of 15 centimeters. What is that charge Q, assuming V is equal to infinity at an infinite distance? So again, going back to the whiteboard and clearing it, you have V is equal to KQ over R. And so we're asked to solve for Q. So Q is equal to R times V divided by K. So we're told R is equal to 15 centimeters. Again, Q is in coulomb. If we want to express Q in coulombs, we need to keep everything in standard SI units. So we'll write that as 0.15 meters. The voltage, and the sign matters, is positive 185 volts. Which means that if you go from an infinite distance to 15 centimeters away, you've gone through a potential difference of positive 185 volts. So the sign matters. And you're dividing by K. And to two significant figures, we can write K as 9.0 times 10 to the 9 Newton meters squared per coulomb squared. And so you plug those values in, you get 3.1 times 10 to the negative 9. And that would be in coulombs if everything else is in SI units. So 3.1 times 10 to the negative 9 coulombs. And so that's the charge that's involved, and it's positive. So again, you're approaching the positive charge, you're increasing the electric potential. And that's basically what that means. You go from infinity to 15 centimeters away from a positive charge, you've increased the potential. Okay, so let's go back to the lecture notes or to the slides. Now, again, this goes back to what I was talking about before. As the problems become more complicated, sometimes it's easier to calculate the electric potential than it is to calculate the electric field. Because the electric potential is a scalar quantity, you don't have to worry about three different components. It's just the one value. And so there are no superposition principle involved with the potential. So if you have multiple points charges or a distribution of charges to figure out the electric potential at a given point, you don't have to add components together or do vector addition. You're just adding the potential from each individual charge together. And so it's a little bit simpler to work with potential than it is to work with electric fields. Having said that, if you have a continuous distribution of charges, you're still going to need to do some integration. Again, here you don't need to worry about directions. And so not having to deal with the vectors does simplify the integration a little bit. But you still have, you're integrating K, or 1 over 4 pi epsilon naught, times the element of charge divided by R, where R is just the distance from the element of charge to the point where the potential is being evaluated. So it's a little bit simpler than working with electric field for a number of reasons. So let's move on then from electric potential to electric potential energy. So the potential energy of a test charge QT located at a distance r from a source charge QS is given by U is equal to K times QS times QT, so the product of the two charges, divided by the distance between them. You can also write this as the test charge multiplied by the potential difference at the point where the test charge, or multiplied by the electric potential at the point where the test charge is. So, and the second version applies universally. So if you've already figured out the electrical potential at a given point, you put a test charge at that point, you multiply the test charge by the potential, you get the potential energy at that point. So how is this similar to the gravitational potential energy, and how is it different? So if you remember going back to physics 130, whatever your equivalent was, the gravitational potential energy defined as 0 at infinity was equal to negative capital G, a universal constant, multiplied by the product of the two masses involved, divided by r, the distance between them. So here you have a universal constant multiplied by the product of the two charges involved, divided by the distance between them. So you can see there are some similarities. One important difference is that with gravity, the potential energy is always negative, meaning that as you approach, as one object approaches another object, the gravitational potential energy will always decrease. And it will always decrease because the force between them is always attractive. In electricity, that is not the case. That if the two charges are the same, whether they're both positive or both negative, if they have the same sign, that product of the two charges is going to be positive, which means if you bring them closer together, they're going to gain potential energy. Whereas if one is positive and one is negative, then the potential energy is negative. So you bring them closer together, you're going to lose potential energy. And so you lose potential energy when the force between, when you bring two attractive objects toward each other, or when you bring two repulsive, when you pull repulsive objects away from each other, you lose potential energy. You gain potential energy when you bring two repulsive objects towards each other, or when you move two attractive objects away from each other, you gain potential energy. And that's true whether you're talking about gravity or whether you're talking about electricity. So with gravity, you lift an object away from the Earth's surface, it's losing, or rather it's gaining potential energy. So if you were to move an electron away from a positive charge that's attracting it, it's gaining potential energy. And if you let it go when it moves towards that positive charge, it's going to lose potential energy. Just like if you let an object that you're holding in the air, if you let it drop, it's going to gain potential energy, or rather it's going to lose potential energy, excuse me, as it falls, and gain kinetic energy as well. So there are some parallels and there are some differences. Again, the most significant difference is that gravity is universally attractive. Electricity can be attractive or it can be repulsive. So let's do an example. How much work must be done to bring 3 electrons from a great distance apart to within 1.0 times 10 to the negative 10 meters from one another at the corners of an equilateral triangle? So let's look at that. So the problem is asking you for the amount of work that's to be done. But this is a non-conservative force. So it's a non-conservative force. You're basically forcibly bringing, 2 objects towards a third. And so the work done by a non-conservative force is equal to the change in kinetic energy plus the change in potential energy. And in this case, we're holding them still, more or less. We're starting with 1 at whatever point it was initially, and then we're moving another point into place and holding it there, and then moving another point into place and holding it there. And that tells you the equivalent amount of work done. And so when you're holding these things in place, there's no kinetic energy involved, or there's no change in kinetic energy involved. You're starting at 0 and you're ending at 0. So there may be kinetic energy at different points along the way. But the delta K is 0. You're taking the electron from wherever it is, and you're moving it to wherever you want it to end up. And then you're holding it in place. So we're not going to be concerned with delta K. We are going to be concerned with delta U. So we have 3 electrons, and we're bringing them to an equilateral triangle. And they each have distance of 1.0 times 10 to the negative 10 meters. So that's how far they are from each other. And so it's an equilateral triangle. So we'll assume that the electron at point 1 was there to begin with. And, so that we're holding that in place. So we're not doing any work to hold it in place. But we are going to do work to bring point 2 from an infinite distance away, or from an approximately infinite distance away, to where it's 1.0 times 10 to the negative 10 meters away from 1. So the work done to put point 2 into place is equal to the change in potential energy. So it's gaining potential energy. Again, you have 2 negative charges, they repel each other. So it's equal to K times Q2 times Q1 divided by R. Because it's the change in potential energy that's involved. And so and we are working in 2 significant figures. So that's 9.0 times 10 to the 9 Newton meters squared per Coulomb squared. And then Q2, and so they have the same charge to both electrons, so it's negative 1.6 times 10 to the negative 19 coulombs. You're squaring that term, so the negative will cancel out. And you're dividing by 1.0 times 10 to the negative 10 meters. Now keep in mind that you're not squaring the denominator, that when you're talking about potential or potential energy, you're dividing by R, not by R squared. So 9 times 10 to the 9 and so that gives 2.3 times 10 to the negative 18 joules. Now, what is the work? Now we're holding charge 1 and charge 2 in place, and we're bringing charge 3 in. So that's going to gain a potential energy. And here's the advantage to working with scalars as opposed to vectors. You're just adding the potential energy due to this charge and the potential energy due to this charge together. And so it's the same magnitude charge and the same distance. So the work done to put 3 in place is just 2 times your answer you got here. So that's 2 times 2.3 times 10 to the negative 18 joules, which is equal to 4.6 times 10 to the negative 18 joules, which means the total work done in putting these 3 objects together in this configuration, you just add W2 and W3 together. And so that gives 6.9 times 10 to the negative 18 joules. So that's the potential energy. So again, you're just, the work that's done or that's required to move those three into that configuration is equivalent to you take one, you hold it in place, you take particle 2, you put it next to particle 1 at the right position and hold it in place, and then you take 3 and you put it in position and you hold that in place. And so you figure out the potential energy that's been gained in the process. So the work you do on 2 is equivalent to the potential energy it gains. The work you do on 3 is equivalent to the potential energy it gains. And so you add that total amount of work together. And again, because you're working with scalars as opposed to vectors, the math is a little bit simpler. So that brings us to an important definition. And this comes into play if you move on to take modern physics. This will come into play a lot. If you do anything involving quantum mechanics, this is an important value to know. And so if you're doing electrical engineering, this is probably a value you're going to need to know. And certainly if you're going into, if you're going to be taking advanced physics courses, you're going to need to know this as well. So the electron volt is the amount of kinetic energy that an electron gains as it travels through a potential difference of +1 volts. And so if it's, if you're gaining a certain amount of kinetic energy, you're losing the same amount of potential energy. So that's equal to Q times the potential difference, which is 1.602 times 10 to the negative 19 joules. So that's the amount of kinetic energy you gain, and that's the amount of potential energy you gain. Okay, I'm back again. So let's go to an example. What potential difference is needed to give a helium nucleus? And so for those of you who don't know, a helium nucleus is an alpha particle. So this is important as far as radiation goes. Q is equal to 3.2 times 10 to the negative 19 coulombs. The helium nucleus has 2 protons, and it's separated from its electron, so it carries a positive charge. And so that's the equivalent of 2 protons. And so we're giving the helium nucleus 125 kiloelectron volts of kinetic energy, and we're asked what potential difference is needed to do that. So let's, again, visualize this and draw it up. So you have the helium nucleus. And it has a charge of +2e. And it's being accelerated. So that's equivalent to being pushed away from positive charges or drawn towards negative charges. So to accelerate a helium nucleus, you're going through a decreasing potential. So delta V is equal to Q, or rather delta U is equal to Q delta V. But delta U is also equal to negative delta K. Again, if there's only the electrostatic force working, delta U is equal to negative delta K. So the potential difference is equal to negative delta K over Q. Now I'll show you a little trick. You don't really need to do the full calculation out on this. So that's negative, and the delta K is 125 kiloelectron volts. and you're dividing it by Q. Now, if you wanted to convert this to joules, you would multiply, well, first by 1,000 to get it to electron volts, and then by 1.6 times 10 to the negative 19. But Q is 2 times 1.6 times 10 to the negative 19. So you can write that as positive 2e and save yourself some math. I mean, there's no point in going by or multiplying numerator and denominator by both by 1.6 times 10 to the negative 19. But if you write the energy in electron volts or in kiloelectron volts, and then in Q as in multiples of E, you would get simply out negative 62.5 kilovolts. So that's the potential difference that it takes to accelerate an alpha particle. And again, a positive charge is accelerated through a negative potential difference. It's pulled to what attracts it, basically. And a negative charge is accelerated through a positive potential difference. And that brings us to our last slide of the day. And other facts about a potential: the electrical potential is constant within a conductor. So remember, the electric field is 0 within a conductor, and the electric field is a measure of how much the potential is changing. So if the electric field is 0, that means the potential is constant inside a conductor. What that value is depends on where you define the potential to be 0. But that's something to keep in mind. One of, I forget whether it's the homework or the recitation problems, deals with that. So the electric potential is constant within a conductor. The equipotential is a line of constant potential, and this comes into play in one of your lab experiments. You're going to be mapping out equipotentials and then inferring the electric field lines from that. The equipotentials are always perpendicular to electric field lines. And the reason for that is that if the potential is constant, going back to the equation up here, that, if you were to draw a line and the potential was constant along that line, that would mean the derivative would be 0 along that line. And that would mean the component of the electric field that points in the direction of the equipotential is 0, which means there's only a component that's perpendicular to the equipotential. And so the electric field lines are, as a result, always perpendicular to equipotential lines. So with that, we're going to be done for today. Done for this lecture. So this was chapter 23. The next chapter is chapter 24, which we're going to apply potential difference to elements of the circuit, starting with a capacitor. And after that will be the second of our 4 exams. So till next time.